November 26, 2010. A Friday evening in northern Italy. 13-year-old Yara Gambirasio leaves her gymnastics practice in the small town of Brembate di Sopra and vanishes into the cold winter night. Her mother expects her home in 10 minutes. It's less than a mile walk. But Yara never arrives. For 3 agonizing months, her family waits. Searches turn up nothing. Then, on February 26, 2011, a field worker in Cignolo di Isola discovers something in an overgrown field about 7 miles from where Yara disappeared. It's her body. She's been there the entire time, through winter snow and ice. On Yara's jacket, investigators find something invisible to the naked eye but more powerful than any eyewitness. DNA. Just a few microscopic cells from an unknown male. They have no idea who it belongs to. They don't even have a suspect. What they're about to do to find this person will push forensic science to its absolute limits and spark a controversy that continues to this day. This is the story of how a murder investigation became one of the most technologically advanced manhunts in history, and what it reveals about the incredible and sometimes terrifying power of modern DNA science. Let's dive in.to understand how investigators would eventually identify Yara's killer. We need to talk about what happened to DNA science around 2010. Because right when this case began, forensic genetics was experiencing a revolution. For decades, crime labs had relied on a technology called capillary electrophoresis to analyze DNA. It worked by looking at short tandem repeats. Think of them as genetic stutters, places where your DNA repeats the same pattern over and over. The old technology would measure the length of these stutters. It was reliable, but it had serious limitations, especially when dealing with tiny, degraded samples. Then came next-generation sequencing, or NGS for short. Instead of just measuring the length of those genetic markers, NGS actually reads the sequence itself. Millions of genetic reads in a single test. And here's why that matters. NGS doesn't just identify a person. It can reveal their ancestry, predict their physical appearance, even estimate their age, all from a sample the size of a few skin cells. The difference between the old and new technology is staggering. Traditional methods needed relatively large, pristine samples. NGS can work with degraded evidence, tiny quantities, even mixed samples from multiple people. It can analyze both nuclear DNA and mitochondrial DNA in the same workflow. And crucially, it can detect variations within genetic markers that the old technology completely missed, variations that help solve the most complex cases. While NGS was revolutionizing what DNA could tell us, another technology was revolutionizing when we could get answers. It's called rapid DNA. Picture this. An officer arrests someone at 2 a.m. In the old days, they take a cheek swab, send it to a lab, and wait weeks or even months for results. By then, the suspect might be long gone. But with rapid DNA, the officer swabs the suspect's cheek, puts it in a machine that looks like a large printer, and in about 90 minutes, while the suspect is still in the booking station, they have a complete DNA profile. That profile immediately gets searched against CODIS, the FBI's combined DNA index system. But it also searches something else, DISC, the DNA Index of Special Concern. This is a specialized database containing DNA from unsolved violent crimes, murders, sexual assaults, kidnappings. If there's a match to one of these cold cases, investigators get an alert immediately. Think about what this means. A serial offender gets picked up for something minor. Before they can be released on bail, investigators discover they're wanted for an unsolved murder 3 states away. The notification happens in real time, while the suspect is still in custody. That's the power of rapid DNA. Compresses months of waiting into minutes. But there's a catch. This technology is so automated, so fast, that it's happening outside traditional forensic laboratories. It's happening in police booking stations. And that raises serious questions about quality control, contamination prevention, and accountability. Questions we'll come back to. Back in Italy, investigators had that DNA from Yara's jacket. But they had nothing to compare it to. No suspect, no database match. So they did something extraordinary and deeply controversial. They launched one of the largest mass DNA screenings in history. Over several months, investigators collected DNA from over 18,000 men in the region. They were looking for anyone who fit the general profile, men who lived or worked in the area where Yara disappeared, who had access to that location, who fit a certain age range. They called the unknown perpetrator Ignoto 1, unknown male number 1. Imagine the logistics of this. Every sample had to be collected by trained personnel. Every sample needed a unique identifier. Every sample required explicit written consent and detailed chain of custody documentation, a paper trail showing exactly who handled the sample, when, and where it went. Because if that chain breaks at any point, if there's any gap in the documentation, the evidence becomes inadmissible in court. The entire case could collapse. The chain of custody isn't just a formality. It's the most critical procedure determining whether evidence can be used at trial. The documentation must include the circumstances of collection, the name and signature of every person who handled it, the period of their guardianship, storage conditions, and the exact time of every transfer. Miss one signature, lose track of the sample for even a few hours, and the defense can move to have the entire evidence excluded. And here's where modern forensic science creates an impossible dilemma. These new DNA technologies are so sensitive they can work with incredibly tiny samples, sometimes just a few cells. But that's also the problem. When your sample is that small, analyzing it often means using it completely. There's nothing left for the defense to independently test. This is exactly what would later happen in the Yara case. The original DNA sample that eventually identified the killer was so small that testing it exhausted the evidence entirely. When the defense later demanded their constitutional right to independent verification, there was nothing left to test. Think about the implications. The state has evidence that supposedly proves guilt beyond reasonable doubt. But the defense can never challenge it, never verify it, never have their own experts examine it. The evidence becomes simultaneously the most powerful proof and completely unchallengeable. Does that sound like justice to you? This isn't just a theoretical problem. It happens all the time with low copy number DNA analysis, techniques designed to amplify signals from minute quantities of genetic material. These methods increase the number of amplification cycles to boost the signal, but they also increase the risk of errors. Stochastic effects, they're called. Allelic drop-in, where false genetic markers appear. Allelic dropout, where true markers disappear. And massive contamination risk. Some jurisdictions have rejected low copy number techniques entirely because the results can be unreliable. The science is there, but the procedural safeguards haven't caught up. And when you combine unreliable techniques with evidence that can't be retested, that's a recipe for wrongful conviction. After testing thousands of samples, investigators finally got a hit. But not a direct match. Something stranger. They found a man whose DNA was similar enough to suggest a family connection. He was a distant relative of Ignoto 1. This opened a new avenue, genetic genealogy. By analyzing this relative's DNA and building out family trees using public records, birth certificates, marriage licenses, investigators began mapping an entire family network. They were using the relative's genetic information to triangulate toward the actual perpetrator. The methodology here is fascinating and invasive in equal measure. Investigators look at patterns of genetic similarity to estimate relationships. Third cousin, second cousin once removed. Each relationship has a characteristic genetic signature. Then genealogists take over, digging through decades of public records, constructing family trees that can span hundreds of individuals. Eventually, this genealogical investigation led them to a bus driver named Massimo Bassetti. When they secretly obtained his DNA and tested it, it matched. After more than 3 years, they had found Ignoto 1. But how they got that DNA, and what they did with it, would become the center of a controversy that continues today. The technique that helped crack the Yara case represents a fundamental shift in criminal investigation. It's called investigative genetic genealogy, or IgG, and it's the same science that helped solve America's Golden State Killer case in 2018. Here's how it works and why it's so powerful and so controversial. When investigators have DNA from a crime scene but no match in criminal databases, they can now create a high-density genetic profile using hundreds of thousands of genetic markers called SNPs, single nucleotide polymorphisms. These are tiny, single-letter variations in your genetic code that make you unique. They upload this profile to public genealogy websites like GeneMatch, usually under a pseudonym. The site's algorithms then search through millions of consumer-uploaded profiles, looking for genetic similarities. The software predicts the degree of kinship. Maybe they find a third cousin, maybe a second cousin once removed. Then, trained genealogists take over. They build family trees, sometimes going back generations, using public records, obituaries, census data, even social media. They narrow down the possibilities until they identify someone who fits the geographic and behavioral profile of the perpetrator. This technique is incredibly effective. Since 2018, investigative genetic genealogy has helped solve hundreds of cold cases. Murders that had been unsolved for decades suddenly have suspects, trials, convictions. Families finally get answers. But it comes with a cost that nobody really agreed to pay. Here's the thing that should make you deeply uncomfortable. When your relative uploads their DNA to one of these sites, they're not just sharing their genetic information. They're sharing yours too. Your genetic privacy is now controlled by every distant cousin who's curious about their ancestry. You never consented to be in a law enforcement database. You never agreed to genetic surveillance. But if your third cousin did a DNA test for fun, investigators can use that to map your entire family tree and place you at a crime scene. The genetic data from one person creates what researchers call an involuntary privacy burden on their entire familial network. You become instrumentalized in law enforcement efforts without your knowledge or consent. Your genetic information becomes investigative evidence, and you have no say in the matter. After the Golden State Killer case made headlines and people realized what was happening, companies like GeneMatch scrambled to create privacy policies. In May 2019, they switched to an opt-in system. Users now have to actively choose whether law enforcement can access their genetic data. The site now emphasizes that it doesn't store raw DNA files. They're deleted after the genetic information is encoded. They collect profile information, contact data, and commercial information, but users control whether they can be shared with law enforcement through their opt-in settings. But here's the problem. By the time these policies changed, millions of profiles were already uploaded. The genetic genie was already out of the bottle. And even with opt-in policies, all it takes is one relative who says yes, and your entire family tree becomes searchable. This raises a massive Fourth Amendment question. The Fourth Amendment protects you from unreasonable searches and seizures. Traditionally, courts said you lose that protection when you voluntarily share information with a third party. It's called the third-party doctrine. Under this doctrine, if you give information to a company, you've voluntarily surrendered your privacy interest in it. The government can access it without a warrant. For decades, this meant police could get your bank records, your phone records, even your email metadata without probable cause. But in 2018, the Supreme Court decided a landmark case called Carpenter versus United States. Police had obtained 127 days of someone's cell phone location data without a warrant, using a court order that required a lower standard than probable cause. The court ruled 5-4 that this violated the Fourth Amendment. Why? Because the sheer aggregation of data over time reveals intimate details of someone's life that deserve constitutional protection. The court recognized a narrow exception to the third-party doctrine. They acknowledged that modern technology creates detailed records that are fundamentally different from the phone bills or bank statements the doctrine was created for. Legal experts argue that genetic data deserves even stronger protection than cell phone location data. Your location changes day by day, but your DNA? That's permanent. It's generational. It reveals not just who you are, but who your parents are, who your children are, what diseases you might get, even aspects of your physical appearance. DNA is the most intimate information about you that exists. And unlike cell phone data, which reflects your choices, where you go, who you call, your DNA is something you can't change. You didn't choose it. You can't modify it. It's fundamentally who you are at a biological level. Yet right now, in most jurisdictions, police don't need a warrant to search your genetic relatives' DNA profiles. Some legal scholars argue this is unconstitutional under Carpenter. They contend that using genetic genealogy to map entire family lineages constitutes sustained technological surveillance of a family unit. and should require a warrant based on probable cause. But the courts haven't settled this yet. The law is playing catch-up with technology that's advancing faster than the legal system can respond. It's not just happening in one country. Interpol now runs a global DNA database where member countries can submit profiles to search for cross-border crimes. The system helps create hits, matches between crime scenes or between a person and a scene, where no prior connection was known. To protect privacy, profiles are submitted as alphanumeric codes without names attached. Member countries retain ownership of their data. But the system still enables global genetic surveillance on a scale that was unimaginable 20 years ago. Interpol even created a separate system called iFamilia specifically for identifying missing persons across international borders using family DNA matching. It operates separately from criminal databases, and relatives must provide explicit consent for their data to be used in international searches. But it's the same technology, the same methodology, applied on a global scale. The infrastructure for worldwide genetic surveillance is being built right now, case by case, database by database. And most people have no idea it's happening. Modern DNA analysis creates evidence so complex that human experts can't interpret it anymore. Especially when you're dealing with DNA mixtures, samples that contain genetic material from multiple people. Maybe it's a gun that 3 people touched. Maybe it's a piece of fabric that has degraded DNA from both the victim and attacker. Maybe it's a sample that's been exposed to heat, moisture, or UV radiation for years. These complex mixtures used to be nearly impossible to interpret with any certainty. Now, we have probabilistic genotyping software, PGS for short. Programs like STIRMIX use sophisticated algorithms to calculate the probability that a specific person contributed to a mixture. The software models thousands or millions of possible scenarios and outputs a likelihood ratio. How many times more likely is it that this person contributed to the sample versus a random stranger? In one federal case, United States versus Gisentainer, STIRMIX analyzed DNA from a firearm and concluded the defendant was 49 million times more likely to be a contributor than a random person. 49 million to 1. That sounds pretty definitive, right? This is powerful evidence. DNA mixtures that would have been declared inconclusive 10 years ago can now be analyzed with mathematical precision. Cold cases that stalled because the evidence was too degraded or too mixed can now move forward. The software can deconvolute complex samples that no human analyst could untangle. But here's the catch. These programs are proprietary. The source code is secret. The defense can't examine the algorithm. They can't verify the assumptions built into the software. They can't check for bugs or coding errors. Defense attorneys argue this is fundamentally unfair. How can you challenge evidence when the method used to generate it is a corporate secret? It's like being convicted by a black box you're not allowed to open. This isn't just a philosophical objection. Software has bugs. Algorithms have assumptions. If those assumptions are wrong, if the software is modeling the data incorrectly, it could produce misleading likelihood ratios. And if the defense can't examine the source code, they can't identify those errors. In the Gisentainer case, despite that 49 million to 1 likelihood ratio, the court ultimately ruled that the specific STIRMIX analysis didn't meet reliability standards for that particular case. Not because the science was inherently wrong, but because the implementation and transparency didn't pass constitutional muster. The court was applying something called the Daubert standard, established by the Supreme Court in 1993. Daubert replaced an older standard called Frye, which just asked whether a scientific method was generally accepted in its field. Daubert is more rigorous. It requires judges to act as gatekeepers, evaluating scientific evidence before letting a jury see it. They have to consider multiple factors. Can the method be tested? What's its error rate? Has it been peer-reviewed? Is it generally accepted in the scientific community? These standards were created for things like drug testing and ballistics, relatively simple, well-understood sciences. Now they're being applied to machine learning algorithms analyzing billions of genetic data points. The law is struggling to keep up. And here's the really tricky part. Most states use the federal Daubert standard, but 7 states still use the older Frye test. So whether your DNA evidence gets admitted in court might depend on which state you're in, not on how reliable the science actually is. There's another problem with ultrasensitive DNA analysis: contamination. When you can detect DNA from just a few cells, you can also detect DNA that was accidentally transferred during collection, during lab processing, or even during manufacturing of the collection swabs themselves. Contamination is defined as the introduction of extraneous DNA or biological material at any point in the process, and it's a critical threat to the reliability of forensic evidence. This is why forensic labs maintain something called an elimination database, a collection of DNA profiles from everyone who might come into contact with evidence. Lab technicians, crime scene investigators, evidence clerks, even the manufacturers of forensic supplies. If contamination happens, labs need to be able to identify and eliminate it. Labs also follow strict procedural safeguards. They analyze evidence samples before reference samples to prevent cross-contamination. They use blank controls to monitor for contamination in reagents or work areas. They conduct validation studies to establish performance limits and reproducibility for every technique, especially those dealing with low amounts of DNA. But what happens when evidence is processed in the field, not in a controlled lab environment? Rapid DNA stations at police booking desks don't have the same contamination controls as forensic laboratories. There's no specialized staff, no dedicated clean rooms, no elimination database checked against every profile. A single procedural error, a single instance of cross-contamination at a booking station, could generate a false DNA profile that gets uploaded to national databases and potentially leads to a wrongful arrest. The speed and convenience of rapid DNA comes with risks that the system hasn't fully addressed. Massimo Bassetti was convicted of Yara Gambirasio's murder in 2016. The DNA evidence was presented as definitive, damning proof. But the case remained deeply controversial, and it still is today. Remember that procedural problem we talked about earlier? The original DNA sample was completely consumed during testing. The defense never got to independently verify the state's findings. They couldn't exercise their constitutional right to independent representation during analysis because the testing happened before Bassetti was officially identified as a suspect. This created a due process nightmare. The investigation was robust and intensive, one of the most exhaustive in Italian criminal history. But when the forensic analysis consumes the entirety of a finite microscopic sample, it renders the state's finding unchallengeable by the defense, regardless of how reliable the initial analysis was. The defense filed appeals. They requested evidence review. They even initiated an investigation into the chief investigator regarding potential misdirection. But there was no physical evidence left to examine. But the controversy goes even deeper than that. During the investigation, analysts also looked at mitochondrial DNA from the sample mtDNA, which you inherit exclusively from your mother and which can help trace maternal lineage. Here's where things get strange. The mtDNA from Ignoto 1 didn't match Massimo Bassetti's mtDNA profile. Think about what this means. The nuclear DNA said one thing. The mitochondrial DNA said something else. How is that possible? The defense argued this discrepancy raised fundamental questions about the evidence's reliability. Maybe the sample was contaminated. Maybe it was from multiple sources. Maybe the analysis was flawed somehow. The prosecution had explanations, technical reasons why this might happen. But the defense could never independently verify any of it because there was no sample left to test. This is the procedural conflict at the heart of modern forensic science. The necessity of robust investigation versus the constitutional requirement for adversarial due process. When you have techniques sensitive enough to work with a few cells, and analyzing those cells destroys them, how do you balance the pursuit of justice with the rights of the accused? Bassetti maintains his innocence to this day. Appeals continue. And regardless of what really happened in Yara's case, whether the conviction is sound or not, it highlights something crucial: the human cost when these systems fail. When someone is wrongfully convicted, and we know this happens because DNA evidence has exonerated hundreds of people, the consequences extend far beyond their time in prison. DNA technology has actually proven to be the most reliable tool for achieving exoneration. It authoritatively rules out individuals wrongly identified by less reliable evidence, like flawed eyewitness testimony. Since the advent of DNA testing, hundreds of people have been freed after years or decades of wrongful imprisonment. But even after exoneration, they face what researchers call stigma, negative societal attitudes and discrimination based on their criminal record. The conviction is a type 1 error in the justice system, a false positive, but it imposes severe informal sanctions that negatively correlate with the person's productivity and capacity for reintegration into society. Nearly 40 states have compensation laws for the wrongfully convicted, but the standards vary wildly. Some advocacy groups push for a minimum of $70,000 per year of wrongful imprisonment. But how do you compensate someone for a decade of their life? For the destruction of their reputation? For the family relationships that were shattered? For the career that never happened? For missing your children growing up? There's a push now for what experts call stigma-free language and dialogue, ways of talking about exonerated individuals that facilitate their reintegration into society rather than perpetuating the harm. Because the legal system can overturn a conviction, but it can't erase the social consequences that follow someone forever. Financial compensation is important, but it doesn't address the intangible harm. The trauma, the loss of identity, the difficulty trusting institutions that failed you. Advocacy organizations argue that comprehensive, structured support services are necessary, trauma-informed counseling, job placement assistance, help navigating bureaucratic systems, to ensure that legal justice translates into meaningful societal recovery. This is the fundamental tension in modern forensic science. We have technologies that can identify someone from a few skin cells left on a surface 3 years ago. We can map family relationships across continents and generations. We can solve cases that would have been impossible to crack just 15 years ago. Yara's family deserved answers. They deserved justice. And these technologies provided it, or at least they provided a conviction. But these same technologies create new risks. Risks of contamination when the analysis is too sensitive. Risks of procedural errors when the evidence is too small to retest. Risks of false positives when the statistics are too complex for humans to verify. Risks to genetic privacy not just for suspects, but for their innocent relatives who never consented to genetic surveillance. Nearly 40 states have compensation laws for the wrongfully convicted, but the standards vary wildly. Some advocacy groups push for a minimum of $70,000 per year of wrongful imprisonment. But how do you compensate someone for a decade of their life? For the destruction of their reputation? For the family relationships that were shattered? For the career that never happened? For missing your children growing up? There's a push now for what experts call stigma-free language and dialogue, ways of talking about exonerated individuals that facilitate their reintegration into society rather than perpetuating the harm. Because the legal system can overturn a conviction, but it can't erase the social consequences that follow someone forever. Financial compensation is important, but it doesn't address the intangible harm. The trauma, the loss of identity, the difficulty trusting institutions that failed you. Advocacy organizations argue that comprehensive, structured support services are necessary, trauma-informed counseling, job placement assistance, help navigating bureaucratic systems, to ensure that legal justice translates into meaningful societal recovery. This is the fundamental tension in modern forensic science. We have technologies that can identify someone from a few skin cells left on a surface 3 years ago. We can map family relationships across continents and generations. We can solve cases that would have been impossible to crack just 15 years ago. Yara's family deserved answers. They deserved justice. And these technologies provided it, or at least they provided a conviction. But these same technologies create new risks. Risks of contamination when the analysis is too sensitive. Risks of procedural errors when the evidence is too small to retest. Risks of false positives when the statistics are too complex for humans to verify. Risks to genetic privacy not just for suspects, but for their innocent relatives who never consented to genetic surveillance. And somewhere in all of this progress, we need to answer fundamental questions about privacy, consent, and constitutional rights that our legal system hasn't fully grappled with yet. The Carpenter decision was a step forward. The Supreme Court recognized that the third-party doctrine has limits, that some forms of technological surveillance are so invasive they require a warrant. But Carpenter was about cell phone location data. It was explicitly described as a narrow exception. It doesn't clearly extend to genetic genealogy, to familial DNA searching, to the mapping of entire family networks using publicly uploaded genetic data. Some jurisdictions are starting to create policies. Some require warrants for IgG searches. Some limit it to violent felonies. Some require notification after the fact. But there's no consistent standard, no federal legislation, no Supreme Court ruling that definitively settles the constitutional question. And in the absence of comprehensive regulation, we're left with a patchwork of corporate terms of service and state laws that vary wildly. Privacy protections depend on which genealogy site you use, which state you live in, and whether your relatives opted in or out of law enforcement searches. Critics argue that this instability undermines public trust, opens the door for potential misuse of genetic data, and ultimately compromises citizens' autonomy. They call for enhanced governmental oversight, clear legal standards, and meaningful consent requirements. But here's the counterargument. These technologies solve real crimes. They catch real predators. They provide real answers to families who have waited decades for justice. The Golden State Killer, the Bear Brook murders, dozens of cold case rape kits finally processed and matched, serial killers identified and stopped. Is the privacy cost worth the justice benefit? That's the question we all need to answer. Because right now, we're building this system without really having that conversation as a society. The Yara Gambirasio case shows us both the promise and the peril. DNA science helped investigators identify a suspect after testing thousands of samples and conducting one of the most intensive genetic investigations in history. It demonstrated the incredible power of modern forensic technology to solve seemingly impossible cases. But it also revealed how these technologies can consume evidence entirely, making independent verification impossible. How they raise profound questions about due process that we still haven't resolved. How discrepancies in the data, like mismatched mitochondrial DNA, can create doubts that can never be definitively addressed when the evidence is gone. Yara's family deserved justice. Every victim does. But justice isn't just about solving crimes. It's about ensuring the process we use to solve them respects the rights of everyone involved, including the accused. Because in a world where your guilt or innocence might depend on whether your cousin uploaded their DNA to a genealogy website, where algorithms you can't examine determine likelihood ratios that send people to prison, where evidence is so sensitive that testing it destroys it, we all have a stake in getting this right. The DNA revolution has given us extraordinary tools to catch the guilty. Tools that are powerful beyond anything previous generations could have imagined. Tools that can identify a person from evidence left years ago, that can map families across continents, that can solve cases that were once thought unsolvable. Now we need to ensure those same tools don't ensnare the innocent. We need legal frameworks that match the power of the technology. We need transparency in the algorithms that determine guilt or innocence. We need constitutional protections that recognize genetic information as fundamentally different from other types of data. We need procedures that preserve the right to independent verification even when dealing with microscopic evidence. And most importantly, we need to have this conversation now, while we still have the chance to shape these systems, rather than years from now when the infrastructure is fully built and millions more people are already in the databases. The future of forensic justice is being written right now, case by case, database by database, algorithm by algorithm. And all of us, whether we've taken a DNA test or not, are part of that future. Thanks for watching.